that it will cause periodic dropouts in signal strength if not compensated at the receiver. So without getting into too many details, we started out at FC and we shifted the Doppler effect shifted the frequency to FC1 plus V over C. So when we demodulate, we cannot then demodulate with respect to FC because the true frequency is actually now FC times 1 plus V over C. If we attempt to demodulate with FC, we'll have a leftover sine. We'll have a leftover sine or cos. I think it's cos 1 plus V over C times T term, which will cause the signal to drop out every 1 over 1 plus V over C seconds. This there's a famous situation in which engineers failed to take this into account. There's a space probe called. Has anybody heard of the Cassini mission? So there was a space probe on the Cassini mission. This is a mission to the planet Saturn. The Huygens probe was attached to the Cassini mission, the Cassini probe, and was intended to detach and land on a moon of Saturn. So their original mission plan was that this thing, they were going to release it right at the moon, and it would land, transmit back information, and everything would be fine. So sometime after launch, they realized that the engineers had forgotten that there would be a velocity difference, a considerable velocity difference between the lander and the space probe. They realized quickly that because they had failed to take that into account, and because the radios were not reconfigurable as they might have been, this would cause the complete loss of all data, because basically you get a cycle appearing in the receiver, and it would basically cut off data periodically, and all that you would get would be corrupted and garbage. What they ended up doing was they ended up changing the approach profile to this moon so that the velocity difference between the lander and the space probe was basically 0. So remember Doppler.
Can you repeat that again when the dropouts occur?
So what will happen here? I don't want to get into a huge thing about this, but how do we demodulate? We multiply this guy by sine 2 pi FCT. And the trig identity there is we take the sum and the difference of the sine. The sum will be 4 pi FCT. We get rid of that with the low pass filter. The difference we'll get 2 pi FC 1 plus V over, excuse me, we'll get 2 pi VT over C, which will be still a sinusoid, which crosses 0, which has a period of which has a frequency of V over C. So every C over V seconds, the signal will drop out. Let's do a quick example. So the carrier frequency FC is 1 gigahertz. The velocity with respect to the antenna, the transmit antenna, is 108 kilometers an hour. So in other words, this is U driving down the 401 directly towards the base station at highway speed 108 kilometers an hour. I picked that number for a particular reason. It's because this is exactly equal to 30 meters per second. So what is FC1 plus V over C? Well, we have 1 gigahertz times 1 plus 30 meters per second divided by 3 times 10 to the 8th meters per second, which is equal to 1 gigahertz times 1 plus 3's cancel, and that is 10 to the minus 7 meters per second. Excuse me, 1 plus 10 to the minus 7. So we end up with 1 gigahertz plus 100 hertz. So just slightly above 1 gigahertz. So in the example I said before, if you didn't take this into account in your receiver, you'd get dropouts at a rate of 100 hertz. Every 1/100th of a second, the signal will drop.
So,
Yes.
so you're driving towards the base station?
No, it's important that V has a sign. What happens if you're driving away from the base station?
Sorry, I just got that.
Okay, so if you're driving away from the base station, what would happen? So I said that the sign of V is positive towards the base station. So if you're driving away from the base station, you would have 1 minus 30 meters per second, and this would be 1 gigahertz minus 100 hertz, in other words, slightly lower. So, I mean, think of where do we normally think about the Doppler effect? We think of it in like terms of a train whistle or something, or a horn passing. So if the car is coming towards you, it sounds higher pitch. If it's going away from you, it sounds lower pitch. So higher frequency towards, lower frequency away. Okay. So, what you could do if you had only one path is you could just match the receiver to the Doppler frequency, and then everything would be fine. Then you wouldn't have that dropout, and that's what the designers of the Huygens probe should have done, but didn't. However, as I alluded to previously, if you're in a multipath environment, it actually doesn't. This is not the only thing that can harm you. Even if in multipath, even if transmitter and receiver are stationary, Doppler effects can occur. So now let's say two paths exist. One stationary and one moving.